Hello, students. Today we will learn about materials. Before going to understand the properties, or particularly physical properties of materials, we start with learning the spring system because it will lead us to understand materials in a better way, in a conceptual way. For an example, that we do have a spring, and this spring is attached at one point, and now it is in its, let's say, normal state. And at the end of this spring, there is some mass attached, and this mass is, let's say, M mass. Now, this spring is at its equilibrium position where it is at rest, neither moving down nor moving up. So now, if for an example, we pull this material downwards, meaning that this object downwards, meaning that we are going to extend this spring. So what will be our new position? The new position will be like this kind of a condition. So now we are somewhere over here, for an example, that we have actually extended from our mean position O to some position, let's say A. So what we did in this way, we actually covered some displacement, and displacement is x. Sometimes we also actually call it E extension. Okay, now what will happen that when you will be pulling this spring downwards, that means you will be applying force downwards, and this spring will try to oppose your applied force, and in that way you can say that the spring is in fact applying the force upwards. And then the force F of the spring, let's call it Fs, that the force of spring. This force of spring will be more and more as x is increasing, meaning that the spring force will be increasing as x is increasing. So this means mathematically that our spring force Fs is directly proportional to the extension. Now, if, for example, we will release this spring will move upward under the action of this spring force. And of course, this spring force is actually completely opposing your applied force. So this spring force is equal to your applied force. So now this spring will be moving backwards. Once it is at its mean position, it will continue its motion because of inertia. And then this spring will actually try to actually apply the force downwards, meaning that now this spring will be stopping its motion. If we ignore all resistive forces, then we would see that this spring will actually go up to a position x naught, and there this displacement will also be the same x. As much you pulled it down, as much it will go back toward the position A prime. So now this spring will be oscillating under the action of this spring force. Now we can very easily understand that the spring force will be directly proportional to the extension in the spring. Now, if we change this proportionality sign into equality sign, then we will get that the spring force is equal to a constant K times X. What this constant K is, that what we call it, that this is the spring constant. This is spring constant. Now, let's try to understand what is the meaning of the spring constant. This spring constant actually have the unit, so you can see from this equation that it is force per meter, meaning Newton per meter. That actually tells us that how much force you need to give extension of a unit displacement like 1 meter. So it means that if, for example, we have a spring and its spring constant is 40 newtons per meter, it means you need to apply 40 newtons to give extension of 1 meter. So this is what is the meaning of spring's constant. Now here, what would happen that we apply the force and we are getting the extension. So this formula can actually explain the function of our spring. Now let's try to plot this formula in the form of a graph, and where along the x-axis we have extension x, and along the y-axis we have the spring force. Now, if you are increasing the value of x, force of the spring will be increasing. It means we will have this kind of a situation. So it means that the gradient of this graph that will be equal to the spring constant, because this is a straight line which follows y is equal to mx, and y-intercept is 0, y is the spring force, x is the extension, then m is the gradient. By comparing this with the equation of the spring constant, or you can say the spring force, then we can see this gradient is the spring constant. Okay, now if, for example, we actually say that here we applied this force and we have the extension up to this point. Now, from this point, what we do, we remove, we actually, you can say, are going to reduce the spring force or reduce the extension. Then what will happen? This spring will be actually coming back towards its original position, to its mean position. So this behavior is, of course, the linear behavior. And this linear behavior, or in simple words, that direct proportionality of a spring force with its extension, that we call it that this is the Hooke's law. This is the Hooke's law. So what Hooke's law actually tells us that the spring force is directly proportional to the extension. So then now, to understand the concept of the Hooke's law and this graph, let's actually translate our this spring system in the form of deformation in the materials or in the system. So here, what we did, we gave an extension that we can say actually what we did, we tried to deform the system. What we did, we tried to deform. So this is deformation. This is deformation in the system. And when we were actually having more and more extension, then it means we were having more and more deformation, and then this system is coming back to its original position. So it means that the system has ability to remove deformation that we actually induced into the system. So if a system have this ability that it can actually remove the deformation, so it can get its original shape, then we would say that this system has elastic properties, meaning that this actually the system is elastic. And in this graph, until we can get this situation of elasticity, we would say that this is elastic limit. This is elastic limit. And Hooke's law is only and only for the elastic limit, or you can say that the Hooke's law can be applicable only for elastic limit. So we can actually also define or state this law that for a material within its elastic limit, the force applied is directly proportional to the extension of the material, or you can say the deformation. So here once again, that what Hooke's law is, the Hooke's law is that for any material within its elastic limits, the force applied, because here you see we understood that we are giving the extension by applying external force, but this spring will actually try to oppose that applied force. So that is why the force of the spring will also be equal to your externally applied force. So we actually can say that up- the force which material is applying against our external force to remove the deformation are equal. And this actually will happen only and only in within the elastic limit. And so then the material will actually come back to its original shape or into its original form. Now, if, for example, we consider that what is happening, that we are going to apply more force, means that we are going to extend this extension. So then what will happen that, for example, we are going up to here at this point. So above the elastic limit, once your system actually crossed the elastic limit, then this graph, it will turn into non-linearity. So why the non-linearity? Let's have a look that what would happen. Now you can also understand, maybe you already have this experience that if, for example, we have this spring and we extend it too much. If we extend it too much, then what will happen? After removing this external force, this spring will not come back to its original shape. Now you can understand that, for example, that here it was the mean position and spring actually it returned actually in the position like this kind of a condition. Now this is actually, you can say, some extension which is still there, meaning the length of the spring has increased. So what now you can say that this is actually the deformation. So this deformation has not been removed. Now, this means that the system is not anymore in elastic limit, because now the system cannot remove the deformation. So materials are actually having some kind of a permanent deformation. So now you can see also from this graph that what would happen, that if, for example, we are here and now we are actually reducing our externally applied force, and then the system will be returning back and it will actually come back linearly. It will come back linearly. Now, what is happening? It would return over here at this point. At this point, what is happening? You can see that there is some actually extension that still your material have. So it means that you still have some kind of deformation, which is now permanently in your material, in your system. So this means that here, when the system is crossing this linearity and entering into non-linearity, then the system will get the permanent deformations, and that region, we call it that this is actually the plastic limits. Now your system is in plastic deformation, or you can say it is in plastic limits. Now, here you actually can also define these two regions in terms of the deformations, that our first, this region. up to this point, linearity. What we do have, we will have elastic deformation. So deformation will be elastic that the material can easily remove. So this is elastic deformation. So the next one will be here. The next one you can see here that this is actually the region of plastic deformation. That is plastic deformation. So this is actually, you could say, very easy to understand, and we can understand this with this spring system, because spring system is a simple system to understand. Now, what so far we discussed? We discussed that the system can have a elastic deformation or the plastic deformation. Elastic deformation when the system's force extension graph is linear, meaning that the force and the extension are directly proportional to each other. Once we have crossed that limit, then it means we are actually forcing our material in a region where it would not be able to remove its deformation completely. It would try to remove what would not be able to remove completely. It means that there will be some deformation left behind. So that what is actually the plastic deformation, permanent deformation. So the Hooke's law, it actually here says that Fs is directly proportional to the extension. So that's why it is only here within this, you can say the linear region. And once your graph is turning in non-linearity, then you are not actually within the limits of the Hooke's law. You have crossed the Hooke's law limits. Okay, so let's consider that we have a material and we are going to deform it elastically. And then how our graph would look like, it would look like as following. For example, we have our y-axis, which is the force, applied force, and x-axis is our extension, and y-axis is applied force. So we know that how the graph would look like, that because our deformation is in elastic limits, so it will be linear. So we are deforming our material elastically. Now, what would happen? You can see that we will have this linear behavior. From this graph, we can also calculate the work done. So what work done is that because you applied the force, and under the action of the force, there is extension, which is displacement. And we know that this work done is force times displacement. Okay, so if this is like this displacement, we can actually see from this graph that the work done must be just the area under the curve of a force extension graph. What the work done is, work done, it tells us transferred energy. It tells us transferred energy. So, meaning that it is telling us that how much energy has transferred from one store to the other. When you are applying the force on the material, on a system, it means you are working on the system. This energy will be storing in the material, and this energy will be storing in the material as a elastic potential energy of the system. This will be elastic potential energy of the system. Potential energy. How can we calculate that? So as we actually looked that the work done is a force times displacement. So it must be the area under the curve. And we can see that within elastic limits, because we are actually having only actually elastic deformation. So the area of the triangle, which is half base, which is extension x, and times height of this triangle, which is applied force F. And now we can say that our this elastic potential energy E is equal to half times extension times this applied force. And from the Hooke's law, we know that F is equal to xk. So we can multiply it with the x. K is the spring constant. Now we can rewrite it half kx square. So this is the formula to calculate the elastic potential energy of a material. So here what we can do, that we have a material and we are applying the external force to extend and keeping the system in the elastic limit. So of course, within the elastic limit, we will be able to have the right value of the elastic potential energy of the system that has stored into the system. Now you can understand that when you are going to actually remove your external force on the system, meaning that when you applied the force externally, you tried to deform the system. And this deformation is linear, meaning that you are having the elastic deformation. As you will remove the force, then the elastic energy which is stored into the system will actually help to put the system back into its original position, into its original position. But if the system has entered into the inelastic limit, meaning non-linear, now you can see that the system is not coming back to its original position, because we will have still some extension. So that formula will be giving some value, but that value will not be the elastic potential energy exactly stored into the system, because above this linear or the elastic limit, the work done is actually going to be used to rearrange atoms of the system. And that rearrangement of the atoms of the system will lead to a permanent or the plastic deformation. So it means that the work that is done, meaning that the transferred energy will be stored as the elastic potential energy of the system until the system is in elastic limit. And above that, the additional energy will be rearranging the atoms for having a permanent deformation. Okay, so this actually the formula is also for the elastic limits. Okay, so let's solve some questions that will actually help us to understand our these learnings of the spring forces and the elastic potential energy stored in a spring, or that would also be the same for the materials. Our first question is that a spring with a spring constant of 7.5 Newton per meter has been stretched by zero point 0.4 meter from its equilibrium position. What is the potential energy now stored in the spring? So what we know the spring constant K, that is equal to 7.50 Newton per meter. And we know the extension in the spring, let's call it X, is equal to 0.40 meters. And these numbers that are given, they also indicates that we need answer up to 2 decimal points. And what do we need to calculate? We need to calculate the elastic potential energy stored in the spring. We know that its formula is E is equal to half K spring constant times square of extension. So this is equal to 0.5 times 7.50 times 0.4 and its square. And if you do these calculations, your answer should be 0.6 joules. So this much energy will be stored in the spring for this much extension. So in the second question, what do we have? A spring that has the spring constant of 800 newtons per meter means that this spring is a bit more tougher compared to our previous question's spring because we need here 800 Newton force to give the extension of 1 meter. And the spring which is given in previous question, it was K is equal to 7.50 newtons per meter. It means we need only 7.50, 7.5 Newton force to give extension of 1 meter. So this is a stronger spring has been compressed. So this time we are compressing it. What the formula will go actually in the same way. And 196 joule of potential energy is stored. What distance from equilibrium has the spring been compressed? So it means we actually know the value of the K spring constant, which is 800 Newton per meter. And this time we are given the energy E, which is 196 joules. What do we need to calculate? We need to actually calculate the extension in the spring. We know the formula of elastic potential energy of the spring E is half kx square. What do we need to calculate? This extension x. So let's rearrange this formula. So this 2, which is dividing the right-hand side, it will times with the energy. So 2 times elastic potential energy. K spring constant is multiplying with x. It will divide to the other side. And x is the square. To remove the square, we need to take the square root. So x is equal to square root of 2 times the elastic potential energy divided by the spring constant. So now we can put the values 2 times 196 divided by 800 and its square root. So what will be the answer? Let's do the calculations using the calculator. So the answer is 0.99. 0.99. So this is extension. So units are meter. So it's almost 1 meter. So let's try the question number 3. In this question, they say calculate the spring constant of a spring that stores 100 joule of energy when compressed to 500 centimeters. So we need to calculate spring constant, elastic potential energy stored in the spring is 100 joules. So remember that in these all questions, the spring remains in elastic limits, meaning the linear behavior of a force extension graph. And then the extension x is 500 centimeters. So it means this extension is 5 meters. Now, the spring constant, again, we know the formula. E is equal to half kx square. This time, we need to calculate the value of the k. So let's rearrange this formula. So again, this 2 will multiply with the elastic potential energy E. Then this x square, which is multiplying, and this will divide the other side of the equation. So x square will be dividing. That will be value of the K spring constant. Now let's put these values. Energy is 100 joules. 2 times of that is 200, and extension is 5. So 5 square is 25. Now you can see that 200 divided by 25, answer is 8 newtons per meter. That will be the value of the extension in the spring. So with these three very simple questions, you can understand that how we can utilize the elastic potential energies concept to do a different calculations. For example, to calculate the elastic potential energy, the spring constant, and the extension. So anyone is missing except other than the given point parameters, we can calculate the missing parameter using this knowledge. So again, remember that this spring constant is actually, you can say the theory of the spring system is actually applicable to the materials for deformation, for elastic and plastic deformation. And this actually, the theory is not only applicable to a smaller systems, but it can also be on a huge system, even you have a bridge. Okay, so let's move ahead. Now we are going to understand the concepts of stress, strain, and Young's modulus. So let's presume that we do have a rod, and this is a cylindrical metallic rod. And for example, it is in this shape. And now we can say that, for example, its lower end is fixed at its position. Now, what we do, we apply the force on this system, and this force can be even compressing it or extending it if it is other way around. Now, in this case, what will happen that if this we can say it's a mean position, then the system will either compress with the actually applied force downwards. And if we will be applying the force to extend it, then this system will be extending to some position depending on the force and the properties of the material. So now, for example, if you are applying this force F here, then you can very easily understand that this force is working on this cross-sectional area A of the system. So this force applied on the cross-sectional area is giving us the value of the stress, meaning that how much stress this system goes under. So the concept of the tensile stress is the following, that the tensile stress is simply the measure of the pressure that you are applying on the system for compressing it or extending it. It means that the tensile stress must be equal to the force divided by the cross-sectional area of the system. And so we write it with the symbol of the sigma, which is tensile stress is equal to the force divided by the cross-sectional area. Now, when you will apply the force on this system, the system will change its length. For example, this we can say that the change in the length delta L here in case of actually extending it or in case of the compressing it. And this extension in our previous discussion, we were writing it as a X. And before putting the system under the force, the total length of this cylinder was, let's say, was the L naught, meaning the original length. Now, this actually, the change in the length relative to its original length, that what we call it the tensile strain. So the tensile strain in the system will be following. It is actually the ratio of our change, our extension, delta L, compared to its original length. Now, let's have a look to the units of these both formulas, the tensile stress and tensile strain. In case of tensile stress, it is force over cross-sectional area. So this is actually the pressure. We know that the units of the force are Newton and units of area are meter square. So newtons per meter square, that are the units of tensile stress, and that is equal to the Pascal, PA. So these are the units of the stress. So you can also understand here that it is actually the pressure. Now, what will be the units of tensile strain? We have change in the length that will be in meters. The original length L naught, it will also be in meters. So meter actually cancelled with the meter. So we can say it is actually the unit less. So no units for the tensile strain. The Young's modulus is simply the ratio of tensile stress to the tensile strain. So Young's modulus, that sometimes we write it with a capital Y or E as well, but here we will write it as a Y because we actually are writing E for elastic potential energy of the system. So the Young's modulus is simply our tensile stress divided by the tensile strain epsilon. So now let's put these values over here. The tensile stress is force divided by the cross-sectional area. So divided by the strain, which will be the change in length divided by the original length. So this will be rearranged as following, that the force times the original length divided by the extension delta L times the cross-sectional area of the system. So here, actually, this Young's modulus is the material's property, which also tells us the stiffness of the material and its response to the externally applied the forces, that it's either it will get the extension or not, or how much extension this system would get. So what the stiffness of the system is. So in simple words, you could say that you can actually also estimate the strength of the material using these calculations by understanding its properties of stress, strain, or in simple words, the Young's modulus. So Young's modulus is a materials property, so that is constant for some for materials.